let's get this. Tan inverse b squared over 2 over I cosine theta minus cosine. I'm substituting for phi. Here is theta plus epsilon minus the other limit cosine theta minus cosine theta minus epsilon over I. Okay? So, and we still have the limit, which is equivalent to I goes to 0. Okay? R goes to B over 2 means I goes to 0. So look at this. Well, I goes to 0, tan inverse something over 0 is what? Something over 0 is infinite. It depends on the sign of the numerator, maybe positive infinite, negative infinite, okay? And tan inverse of this quantity is what? Pi over 2. But again, if it's either positive pi over 2 or negative pi over 2, that's it. So let's look at the sign of this guy. You have an angle theta, you add something to this angle, so it's larger angle. Cosine larger angle is what? Is more or less? Cosine larger angle. What about cosine 60 versus cosine 30? What about cosine 60 versus cosine 0? The cosine decreases, right? Cosine 0 is the largest, okay? So this guy is less, so the subtraction is positive, so this guy goes to positive pi over 2, okay? So this is pi over 2. Whereas here it's the other way around, so this is negative pi over 2. So we're done. The V radial of the cylinder at an angle theta is Q theta. Pi over 2 minus pi over 2 is pi. Cancelling with the pi down is a very simple relation. Is only half of the source distribution. Okay? And we're done. Why? Because I know this guy from the no penetration condition. Now I got my distribution, and if you got my distribution, my V theta was waiting for the distribution. Okay? Please, if you have questions, stop me. I mean, we will do things like this many times, but not with the exact same spirit. Every author has his own spirit, so we will not do this again. I mean, the exact same derivation, of course. We'll do something similar, not the exact derivation. Question here?
Actually, I think my question is perfectly answered after that.
Okay. Okay, so since we did this, let's quickly go on. You know, we have VR cylinder now, which is the 2 sine theta times V motion. This is V motion. Okay? So Q is 2 VR cylinder, right? But this guy was 2 V motion sine theta. So this is 4 V motion of theta sine theta. And our tangential was waiting here, so let's get that down. My V theta at any angle is negative what? 1 over 2 pi, I guess? Okay. 1 over 2 pi, integration from 0 to pi, Q of theta, or Q of phi, sine phi, d phi over cosine theta minus cosine phi. Let's substitute that. Q of theta is from here, so this is 4 V motion of phi sine phi times whatever left from here. We have another sine phi d phi over cosine theta minus cosine phi. Okay? And we have an expression for V motion. Let's carry out this integral. V motion was this guy. So we have some constants, negative u alpha, negative h dot. I'm assuming small disturbance, so you know, sine alpha is approximately alpha. If you don't like to assume small approximation, keep it, but I'm doing the Theodorsen derivation. So usually when we do a little bit larger angle of attack where the sine cosine will matter a little bit, you can keep them, okay? So this is almost unity, okay? So minus h dot plus alpha dot AB and minus alpha dot times x, and I'm reminding you that x is b cosine theta or cosine phi, whatever you call it. So I'll take this and put it here, and I'm reminding you that sine n phi, sine phi, d phi, we already stated this last time, cosine theta minus cosine phi, one of the famous integrals from 0 to pi with this pi is cosine n theta. So if we do this integral, we'll immediately get our V theta as a function of theta is, let's get that. I guess it's 2, and you can see the 2 from where, 4 and 2 here. The pi goes away with the integral. We have this guy, so u alpha plus h dot minus alpha dot AB cosine theta plus alpha dot b over 2 cosine 2 theta. We got the tangential. What was waiting for the tangential? Do you remember? What was waiting for the tangential? Can you remember? Derivation steps. What was waiting? Phi was waiting for the tangential, right? Just integrate the tangential. It's as simple as this, okay? And why phi? Because also the left was waiting for phi. And we're done. Let's do it quickly to get the left expression. So let's integrate that. So we have here phi cylinder at any angle theta is what? Negative b over 2 integration v theta any angle from theta to pi. So this is just integrate, and you can see if you integrate the cosine, you get sine, you get this guy, you get sine 2 over 2, and that's it. So this will give you b here, the same bracket, times sine theta, and this guy divided by 4 now, sine 2 theta. So we got phi. This is great. The left is readily in terms of phi. We just need two things for the left. We need phi trailing edge, which is phi at theta equals 0. This is how much? This is 0. And we need partial phi, partial t. This is the two things that the left need. Integration of partial phi, partial t plus u times this guy. So let's differentiate this with respect to time. So theta is constant. So this will be b, this bracket, here it is, so it's u alpha dot. So you can see here that if u is constant, you will have two terms. Theodorsen did it for a constant u, but if you have time varying free stream, nothing will change, it's the exact same thing, but you will, when you differentiate here, you will have another term. Okay? So u alpha dot plus h double dot. Are you following me or not? I'm differentiating this guy, right? Is this term, is that term, and I'm differentiating this term with respect to time. So this is h double dot. Now I have alpha double dot AB, this is all times sine theta, not touch the sine theta. And I have an alpha double dot again, sine theta. And here is your left, it's waiting. So my left was 2, the formula above. 2 rho times the integration of negative b to b partial phi partial t dx plus u times phi trailing gauge. So you can see that phi trailing gauge is 0, making this is 0. And from this relation, you can see immediately that for a non-circulatory flow, there is no circulation. No circulation. The phi trailing gauge is 0. Okay? So the only source of lift is unsteadiness. If you don't have any circulation, the only way to get a lift force is that you have to have a time varying, explicit time variation of the phi. If your phi is not time varying, then no lift without circulation. Okay? I have this guy, let's just substitute it. And I have this guy as a function of theta, so just turn this into theta. This is negative b sine theta d theta. And here is your lift. Pi rho b squared times u alpha dot h double dot minus alpha dot ab. Another term. Yeah, yes, good. That's it. So this is the non-circulatory lift. Okay. So let's identify these terms first. What is this and what's that? So this term looks like a mass. It has the units of mass per unit length, because well, two-dimensional, everything is per unit length. So you know, it's the density times volume gives you mass, so we're multiplying by volume per unit length or area. So this is a mass. It's actually called the added mass, sometimes virtual mass. And I'll tell you what is it. Virtual mass, apparent mass, sometimes of course non-circulatory. Okay? So this has the units of mass, and this is what? This has the units of what?
Acceleration.
Acceleration. We have h double dot here, right? And alpha double dot. So this is acceleration. That's exactly correct. Can we relate this acceleration to acceleration at a particular point? So this is d by dt for u sine alpha or u alpha, okay? U sine alpha or u alpha h dot minus alpha dot ab, right? This was d by dt for this velocity. This velocity is what? Can you tell me what's this velocity? Recognizing that this is sine and maybe this cosine alpha. What's this velocity? U sine alpha is what? U sine alpha is what? What's U sine alpha? Ah. What is U sine alpha?
Perpendicular.
Yeah, it's the normal speed due to this u at any point. What about h dot? What's h dot? Say h dot cosine alpha. What's h dot? Or h dot cosine alpha, what's that? Again, it's the normal speed at any point due to h dot. So what is, because these two terms, they induce the same normal speed at all points. Alpha is not. Alpha dot is not. So this is the normal speed at what point?
At the hinge.
At?
The hinge.
So alpha is at the hinge. So at the hinge, there is no normal speed due to alpha dot, right? So at what point? Come on, guys. At what point? This is the normal speed at what point? It's at the center. Yeah. Alpha dot multiplies by AB. Here is the AB, so it's alpha dot at this point. It's the normal speed at this point. So this is actually the normal speed at the half chord point. D by dt for it is the acceleration at half chord point. So the non-circulatory lift can be written as, this is actually negative the acceleration, you can see that. Can be written as negative mass, negative the added mass, times the acceleration at the half chord point. So let's think about it. If I have an airfoil and I want to move it. Okay? I want this airfoil to move in this direction with an acceleration A. How much force do you need to act to put this guy to move with acceleration A? How much force? So the force is mass times acceleration. What's this mass? What's this mass?
The airflow mass.
No, I'm saying, yeah, exactly, it's the airfoil mass. Thank you. It's the airfoil mass. Okay? So now what we're saying is that if you want to move this guy in vacuum, this is exactly what you need to exert. But if you're going to move it in air, the air will respond. Why? Because when you accelerate the airfoil, you will need to accelerate the slice of the air immediately in the immediate vicinity of the airfoil, very close to the airfoil. You need to accelerate so at the beginning, if the surrounding air is stagnant and you're going to accelerate this guy, you will need to accelerate this surrounding fluid. How much is need to be accelerated? Well, according to this theory, it's this exact mass. And this exact mass is the mass of what? It's pi rho b squared. It's the mass of a cylinder whose radius is the half chord length. So this is this cylinder of air around the airfoil. It's as if when you move the airfoil, you are required not only to accelerate the airfoil, but the airfoil with the surrounding fluid up to a cylinder of radius half chord length. It's as if you're moving this whole block, the airfoil and the fluid around. Okay? According to this theory. So that now if you're moving in a fluid, how much force you need to exert? Well, it's mass times the acceleration. But what mass now? What mass? What do you think?
The airfoil plus the added.
Exactly. The airfoil